one positive quantity with that, and that positive quantity is telling us that which values are more likely to occur, which values are less likely to occur. So a variable which can have a certain values, but we also know that what kind of values with what probabilities it can take. So whenever, if we are concerned about any outcome, that outcome, whatever we are measuring, let's say we consider time to failure, TTF for reliability. So TTF is a variable. It can have any value. It may be 0, it may be 1 year, it may be 1.5 year, any value. So it's a real variable which can have any set of the values. Now the thing is, we are calling it as a random variable. So though it is a real variable, but if we statistically know that which values are more likely to occur, which values are less likely to occur, so we assign a PDF to it. So we assign a distribution to it. When we assign a distribution to it, it becomes a random variable. So when we say it is a random variable, we are not only knowing the possible ranges, but we are also knowing which values are more likely to occur compared to other one. So here, generally we use a term experiment in our statistics. So experiment term we use to describe the process for generating data, right? Now TTF, how we will know that what kind of distribution it will have, that we will come to only know if we have certain experiment. That means certain data, whatever data we have, once we have the data, then only we can say whether this is a random variable and what kind of values it can have. The variable can only take a certain possible outcomes. So whatever is the range or whatever is the values it can take, all possible values are called as a sample space, right? And any outcome, specific outcome within the variable which a variable can take, that we call it as a sample point, right? Or it's a member of sample space. Why we are discussing this? Because if later on you come across these terms, you understand that what is the meaning of that. Now let's say if we take an example that we are doing one experiment. In that experiment, first we are tossing a coin, right? And we have made a condition that if head comes, then the coin will be tossed again. But if tail comes, then a dice will be rolled, right? So how many, in this experiment, how many possible outcomes are there? Possible outcomes are that in first trial we get head, and in second trial we get head. First trial we get head, second trial we get tail, right? So this is one possibility. Similarly, in first trial we get tail, second we get 1, 2, 3, 4, 5, 6. So this becomes our whole sample space, right? Sample space means all possible outcome, and every outcome here will be called as a sample point, right? So I hope this sample space and sample point concept is understood. Okay. Then comes the term event. Like what we consider in reliability, there are two events: failure event and success event. Right? So failure and success events are the events. They are not simple sample point. They are not. They may be a combination of several possible combinations of occurrences. When they happen, then they can be labeled either as a failure or as a success. So failure and success are the events, not the sample point. But when we call something as an event is called when it's a set of possible outcomes, right? And this set can be one, null, or can be full set. So, but what is the commonality there? That and any set of outcome, we will not call it as an event. Whenever we are calling an event, then there is some properties based on which these events or these sample points are similar, or these all elements of the sample space will be called as a event. So we are not interested much in sample points, but we are interested in events. We want to know events probability, right? So to know the event probabilities, we have to accumulate the sample point probability. Then only we can get the events probability. Like we are interested in an event that if we toss a dice, then the number will be divisible by 2. So that means 3 and 6 will be the sample points which fall for this event. So a set of 3 and 6 will be called as an event. Now let us see that what kind of relationships we generally use in the reliability theory. First is null or empty set. Null or empty set means there is no outcome. That means it's a no sample point is there within this event. So then it will be called null event. When we call union of the two event, let's say this is event 1 and this is event 2. So whenever we make union means all possible outcomes, but no repetition, right? So whatever is outcome is there in E1 covered in E1 and whatever outcomes are covered in E2, all together will be called the union, right? Intersection means the common outcomes, in the two events. Mutually exclusive means there is in the two events, there is no outcome shared. No outcome is common to them. Then we have the containment. Or we can say that E2 is subset of E1, right? Or E2 is contained in E1, right? So it's a subset completely covered in E1. And complement means if an event is there, so in whole sample space, everything which is not covered in E is the E bar or the complement of E. You all know all this, so I'm going a little faster here. If you find any problem, please interrupt me. Then comes counting sample points. Why counting is required? If you see, we are talking about events. So whenever we are saying failure event or success events, many times we need to find that how many such cases are possible. So we need to count the sample points which are covered in an event. So for that purpose, we use this permutation and combination. For example, a voltage divider circuit has two resistors, right? So we generally have voltage divider like this. Okay, R1, R2. Each resistance has 5 states. So this resistance generally can fail in multiple ways. That means working within tolerance, that is the working state. So resistance tolerance is, let us say, 1 kilo ohm plus minus, we can say plus minus 10 ohm, right? So if this value is within this range, then resistance is supposed to be working within tolerance. Failed in short mode, that means the resistance has become short. That means resistance has become 0. Failed in open mode means the resistance has become open. So resistance has become infinite. Reduced resistance, that means resistance is less than 1k minus 1k minus 10. So maybe 0.90 thousand, right? 100, so 1000, one more point. So 0.90, 9990, right? So if it is less than that, we'll call this as a reduced. Increased resistance means resistance is greater than 1.0010, right? I hope I'm correct. Kilo. Sorry, 0.010, right? So 0.9 0.99000. Okay. So this is, so our resistance can have these states, 5 states. So both the resistance can have these 5 states. So how many possible combinations are there? 5 into 5, 25. So that means this voltage divider circuit based on the 5 states of each resistance can have 25 possible states, right? Or 25 possible sample points, we can say, right? Now, out of these 25 possibilities, we have to identify which one are the success states and which are the failure states. So when I say that this is in a success state, then I have to club and I have to find out that all these combinations, 25 combinations, which are the combination the system is considered to be working, so reliable, and which are the combination system is not working, that will be called unreliable or failure state, right? So whenever we are discussing with system states, the counting is required. Some way of counting is required. Permutation, we know it's an arrangement of all part or part of set of objects. So here order is important, right? So which one comes first, which one comes second, that is important. So we can arrange n objects in order, all in order, same, all distinct object. When we arrange, we can arrange them in factorial n ways. But if we want to order only r out of n, then that means out of n we take r places. So so what will happen here? I can write it that total possible cases were factorial n. Out of the factorial n, it is reduced by n minus r factorial. So n factorial n divided by factorial n minus r will give the NPR. Okay. Which can also be said that factorial n divided by factorial r. Okay. Sorry. So this will be the cases. Now the number of distinct permutations of n things, of which n are of one kind, n2 are of second kind, nk are of kth kind. That means if there are similarities, then the similar will reduce. So if let us say we generally use one letter is coming twice, so it will be divided by factorial 2. So same way, whatever is the similarities is there, their factorials will be dividing. Okay. Let's say we take one example that in 1 year we have 3 awards for research, teaching and services, which will be given to 25 graduate students in a statistics department. If each student can receive at most 1 award, how many possible selections are there? So we have 25 students. Out of 25, we can only give 3 awards, right? So first award can be given to any one of 25, but the first one, if he receives an award, then he cannot receive second award. So second award can be given 1 out of 24, and third award can be given 1 out of 23. So that 25 P3 will give us the total number of possibilities in which 3 awards can be distributed. Another concept which is more popular and used in reliability is the combination, NCR. In NCR, whenever we say, what happens that we are partitioning an object, a set of objects into R cells. If we divide it into multiple cells, that's it. One set is N1 contains one, N1 is going into 1, N2 is going, and where summation of N1 plus N2 plus NR will be N, right? So N are celled or grouped into R number of groups. And so each group size, when we, so total number of combinations factorial n divided by each group, because within the group there is no combination, right? Within the group, the sense of order is not there. So that group contain whatever number is there, we will divide by that. So this gives us NCR, but most of the time we are interested in 2 parts only. Let's say we have one bag, we take out R number of ball from N. So how many balls will be of that? How many ways it can be taken out? Similarly, in reliability theory, we are interested in 2 things, failure or success, right? So if we have n number of unit, now they can be in 2 states, either in failure or it can be in success. So how many such possibilities can be there? We are many times interested in that. So whenever n is there and we say what is the possibilities in which R units can be in failure state. So how many such possible combinations are there? NCR, right? And so whenever I say R number are in failure state, then n minus R will be in success state because units can have only 2 states. So this will be factorial n divided by factorial R and factorial n minus R, right? So it did, if you see, if I exchange R with n minus R, that is going to be same. So these both are same, whether I say R failed or whether I say n minus R successful, both will give me the same answer. So this is used in binomial distribution, which we will see. And this is very essential because whenever we are trying to understand these distributions, then we have to use this whenever similar items are there. We'll see that. We'll discuss more about this. This is just kind of revision which you're going through. So how many ways we can have 7 graduate students to be assigned to one triple? So we have group of 3, 1, and two double hotel rooms, right? So room number 1 is having 2, room number 2 is having 2, room number 3 is having 2, right? During a conference, and we have to divide 7%. So how this is possible? Total possible is 7, and out of this individual room, they are lacking any is 2, 2, 3, 2, 2. So that will give us a 210. So the 210 ways, like if you see simple 7%, we are dividing in 3 rooms of 3, 3, 2, 2. There are 210 possible ways in which, distinct ways in which it can be divided. Let's take another example that we have 5 identical units. The system will fail when 3 or more units fail, right? So how many are the total system states and how many of them belong to failure state? So there we have 5 units, right? And each one can have 2 states. So total number of states are 32. First one can have 2, so 2 to the power 5, that is equal to 32. Now we want to know how many are the states in which 3 units are failed. So out of 5, 3 units are in failed condition. So that means we set 3 as failed and we set 2 as successful. So factorial 5 divided by factorial 3, factorial 2. But we are saying 3 or more. So that means 5 are failed. That means 5C4. So factorial 5 divided by factorial 4, factorial 1. And 5C5, all 5 failed. 5 divided by factorial 5. That is equal to 1. Right? This is equal to 5. And this is equal to 5 into 4 divided by 3 into 2. So sorry, 5, 4, 3, 2. So 3, 2, 1 multiplied by 2, 1, right? So 2 and 2 will cancel by 4, 3 will cancel by this, and we will have 10. Okay. So we are able to calculate. Simple ways like 5 is there, 3, 3. So I will write 5, 4, 3, 3 terms here and 3 terms here. So 3, 3, 2, that will be equal to 10. So we can calculate each state and how much total states are there. 10 plus 5 plus 1, 16. That means out of 32 states, 16 states are in failure states. Okay. Similarly, if 16 are failure states, then 32 minus 16, that is equal to 16 states will be in failure states in all these. Here, why we are doing this? Because we need to calculate probabilities later on. And for that, we need to know how many such states are there. Does anyone has any queries here? Anything you want, if you feel that something we are going off, or if you want to relate or something, please put up your query. No queries?
No query, sir.
Okay, everyone knows this, right? Fine. So now let us come to the probability loss. So we know probability is favorable outcome divided by all possible outcomes. While number of samples which we are using for this estimation is very, very high. So we cannot, like, many times what happens, why our estimates are biased, because we have, like, we are experiencing some, we are having some experience with because in my home maybe I'm using one bike, one computer, or one AC, etc. So if I have some problem with that, but I will say this is useless, right? But its probability of failure is high because we have only one out of that. If by chance it fails, we will say, but that will not be defining the exact probability. If you want to say that something is having high failure probability, we should take a large sample size. We have to look at the neighbors, whoever other customers are there. Then only we can say it has to be, the observation has to be made to a larger sample size, because any low probability event can also have a failure. So let's say if I toss a coin 10 times, right? So I get head 4 times, I get tail 6 times. So in that case, if I assume this, then 4 by 10 will be my head probability, and probability of tail will be 6 by 10, 0.4, 0.6. So when my number of samples are small, then if even the coin is unbiased, I may have a probability which is wrongly estimated than the true probability. Therefore, I have to do a sample, large samples I have to do. I have to do it for 100 times, 1000 times. Then my probability estimate of event will be reaching to the true value, right? Because probability is average over a larger number of samples. That is what we have to understand. And that is where the problem comes. That most of the time we are having a biased assessment of opinion because our samples are limited. Okay. So if samples are limited, we have to understand that just taking mean may not be enough. We also have to understand how much is the variability and what is the possible range error in the estimation.
I had a
Yes,
question on this.
please.
Uh, in some cases, actually, because the failure is so risky that we won't have enough sample for those cases. So, how do we define? How do we calculate reasonable um, probability and still have very low sample space?
So here, like generally, whatever we do, uh, effectively, it is not never going to give you a reasonable estimate if you have a lesser samples, right? But we try to augment the lack of the data by certain ways. Like we can look into the history. So similar event or similar experiment which has been done with the similar devices by someone else or by our own earlier experience, then we would like to take advantage of it, and we can use it as a prior information for our next estimate. Then we try to update our old or historical information by the observations which we are having currently. So Bayes theorem is many times used for that. So Bayes theorem is now popular for this. But again, even when we are doing this, there are many issues which we may face. So best way is that to have the data. Whenever we are having lack of data and when we make an assessment of situation, our situation will have more uncertainty. Right? Our assessment has more uncertainty. Uncertainty will reduce as we go for higher number of samples or our experience becomes more and more. So there is no exactly way to divert this, but still we need to have or improve our assessment so we can use historical data, we can use expert opinion as an as a tools for compensating for lack of the number of samples, right? But again, the moment we go for this, there is a biasness. This is away from reality because reality is what we are observing. And but again, in reliability theory, we have to make predictions. We cannot actually observe the failure. So we have to depend on historical data and we have to depend on expert opinion so that in less number of samples, we are able to make a meaningful assessment and improve on the or reduce on the uncertainty, right? Which is there in our estimate. So uncertainty, as we know, like if we are having the X bar assessment, right? So for X bar, sigma of X bar is called as a sigma by root n, right? So if we know number of samples as they increase, then only that whatever uncertainty is there in the estimation of X bar, it will reduce. But if it is not, then we have to use certain other ways to assess it. So there are challenges with that, but can be done. Even if we do, whenever we go beyond true nature, then our prediction error will or the estimation error will be higher. Okay. Is it okay?
Yes, sir. Thank you.
So though there are ways, but we have to be very cautious when we are using. Right? So the sources, etc., should be properly understood. Now this probability which we have, this probability is always a positive quantity and the probability is a value between 0 to 1. and one means it is a certain event. Whenever we experiment or whenever we do this, every time we will observe this, right? Zero means never going to observe. Probability of complement is 1 minus PA, because 1 is the total probability and 1 minus PA will give the probability of event not occurring. So probability of failure will be 1 minus probability of success, or we can say reliability is equal to 1 minus failure probability. There are certain problems whenever we can use these mathematics, one or certain rules, that probability of A union A will remain same. So how many times we make union of the same event, the probability is not going to change. Same way, A intersection A is also going to be A. A is completely common with A. So how many times we do, it is not going to change. But this change philosophy, because generally A plus A becomes 2A, right? But in probability theory, A plus A will not become 2A. A plus A will be equal to, if I say plus is representing union, that will be A only. So if I add the same event with same event again, it will not change. Similarly, all these can be obtained. Similarly, if I say probability into probability, probability of A multiplied by probability of A will be P only. It will not become P square, because A into A is not A square. It is equal to A. Similarly, P plus P is not 2P, it is P. P plus Q is 1 and P dot Q is 0. There are two types of terms which we come across. One is the independent and another is the mutually exclusive. What is meant by independent? As we understand, if two things are independent, that means one will not influence another. Independent means influence is not there, right? So if two events are independent, then what will happen? Whatever is the commonality between the two events happening, this commonality is the natural commonality, because of the, if they are having the larger space or larger probability, then commonality will be higher. If they are having smaller space, then commonality will be smaller. So if they have some commonality, it is by chance. It is not because of dependency on that, right? So we can say that probability of occurrence of A, given that event B has occurred, is not going to influence the probability of A. Probability of A will remain same. Similarly, probability of B will not get influence if A has occurred or not occurred. This will always remain same as PB. Okay. Similarly, two events are called mutually exclusive if they cannot occur simultaneously. That means there is no interaction. So probability of A intersection B is 0, mutually exclusive. So I usually ask one question whether, what do you say, mutually exclusive is independent or not? Please quickly tell me what you think about it. Mutually exclusive.
The possibility, if a coin is tossed, the possibility if heads arise, so there will be no possibility of occurrence of tails.
Yes. So, sorry, I could not get you completely.
So basically, the exclusive events are those events
These two
which
are independent, sir.
any kind of
Okay. Any more?
in things.
How many says independent?
Sir, independent and exclusive events are different, completely
Yes.
different.
But I'm saying if an event is exclusive, mutually exclusive, which category they may belong, independent or dependent?
I believe it is dependent, sir.
They are dependent, right? If let's say, like one example was given, that if I toss a coin, head comes or tail comes. So whenever I'm tossing a coin, if head comes, tail cannot come, right? So they are dependent. If head is coming, then tail will not come. They are dependent. They are like enemy to each other, right? He says that, head says that if you're coming, I will not come, right? So like in a party, two people are going, and he will say, okay, if you're calling that guy, then I will not come. So they are the dependent. Independent means whether someone comes or not doesn't come, I have to decide on my own whether I'm going to this or not. So occurrence of head or tail, occurrence of 1, 2, 3, 4 on dice, or occurrence of failure or success, right? If it is failed, it cannot be success. So both they are mutually exclusive. Since they are mutually exclusive, they are also dependent, right? But if I toss two coins, right, then on one coin, whether it comes head and tail, in second coin, whether it will come head or tail, they are not influenced by each other, right? If first coin gets head, it is not going to define whether it will be head or tail on the second coin. So the two events, that means two independent coins, when I'm tossing, then they are not dependent on each other. Okay? So they are independent. Law of intersection. We want to know the probability of A intersection B. Okay? So probability of A intersection B is probability of A multiplied by probability of. So probability of A, that means we say that event A has happened, right? So let us say this is A, this is B, and this is A intersection B. If A has happened, then this turned out to be B given A. So probability of A multiplied with probability of B given A has happened will give you the probability of A intersection. Or we can say the reverse, probability of B multiplied with probability A given B has already happened. Both will be same, both will be giving the intersection. But this is the case when events can be dependent. If events are statistically independent, then this will be P B given A will be PB, PA given B will be PA. So we can say this will become PA into PB. That means intersection probability is the multiplication of individual probabilities. They are having intersection because of the they are coming together. The probability is, if they both are supposed to have the high probability, then both will be coming to a party will be same having the high probability. If both are having less likely to come to a party, then intersection probability will also be less. Okay? Or if one of them is having high probability, one of them is having low probability, the total probability will be on an average. They may be meeting in the party or they may not meeting in the party. So this is also called multiplication theorem. And in reliability, we use it for the series system. Okay. What is series system? In series system, we say that we have two elements, let's say A and B. So the system will be reliable only when both of them are reliable. So I took the example of, let's say, voltage divider, right? In voltage divider circuit, if let us say either of R1 or R2, if anyone fails, will the system work? Anyone?
No, sir.
No, sir, not one.
Right? So for the system to work, both has to work, right? That means this is a series system where R1 and R2 both should be in success state, or both should be in reliable. Then only system will be reliable. So how much is the reliability? If I know the reliability of R1, if I know the reliability of R2, let us say that is small r1 and small r2, then I can calculate the reliability of the whole system, that my voltage divider circuit consisting of R1 and R2, how much is the reliability? If I want to count reliability of battery also, then battery also need to be reliable. If battery stops working, then also my circuit will not work. If I want to count wires also here, I can include the wires reliability also. So for this system to work, resistant R1 has to work, resistance R2 has to work, battery has to work, and wires has to work. If any one of them fails, the system will fail. So my system reliability will be series of all this, because all need to work. Then only series system. So for series system, it will be intersection. That is probability that R1 is working, R2 is working, battery is working, and wire is working. So this will be equal to, I will assume, if I assume that all events are independent, right? Why we consider independent? Because it makes our calculation simple. If R1 fails, then it is not impacting the probability of failure for R2. Or if R1 is working, it is not affecting the probability of working or failure for R2, B, and W. So that's why we can say that this is probability of R1 into probability of R2 into probability of B into probability of W. Or I can say that is equal to reliability of R1 multiplied by reliability of R2 multiplied by reliability of battery multiplied reliability of wire. This will give me the system reliability. So for system reliability calculation, we use this law of intersection or multiplication theorem. That probability of intersection is multiplication of the probability of the individual items, assuming that they are independent. Is it understood, everyone? If you have any query? This is called series system. Anyone?
No, sir. As they all are interconnected, we can imagine that they are interlinked. So it's clear, sir. Thank you.
Can you speak little louder? I could not understand.
I was just saying, sir, it is clear. As the
Okay.
dependent and exclusive events are, it is clear.
Okay. And this series system?
Yes, sir.
Right. So law of intersection is applicable to the series system, right? Fine. Then comes union law. Union law is probability of A union B, right? If we have two events A and B, right? We have A section B, right? Now what happens if I want to know union of A and B? That means I have to get probability of this whole event. Now what happens whenever I'm counting probability of A? In that this area A intersection B is coming. When I'm counting probability of B, then again A intersection B area is coming. So what happens? This common area is coming in twice. It is coming in A also, it is coming in B also. But as we know with the probability theory, same thing, probability of A intersection B plus probability of A intersection B is not equal to twice of probability of A intersection B, right? It is equal to probability of A intersection B only, right? So that means I have to, if I'm taking probability of A union B as probability of A plus probability of B, then I have to decrease probability of this area once from here, right? So this becomes minus probability of A intersection B. Is it understood? And if events are independent, then probability of A intersection B is nothing but PA into PB. Okay. If dependent, then we can write this dependency formula. But this we rarely use. We mostly assume independency and we use this formula. If they are mutually exclusive, then what will happen? Intersection will be zero. Probability of intersection will be zero. They cannot be together. So in that case, probability of A union B will be equal to probability of A plus probability of B. But this condition also rarely comes in the reliability analysis. Most of the time, we are working with this, that both events are independent. Because generally we do not use the multiple considerations. We generally use when we are working trying to find out probability for failure, then we talk about events which are failure events. When we are talking about success events, then we talk about the events which are responsible for the success. We generally do not mix the two in same expression, right? So it generally will not come like a mutual exclusive. If I want to say I want to calculate probability of A union B union C, right? So probability of A union B is known to me. Now, if I want to calculate for C, then what will happen? Same formula, A plus B minus AB. So A plus B is already here, A union B. I assume C here. So what will happen? This will add C and this will subtract C intersection with this A. So probability of A intersection C. C intersection with B minus probability of B intersection C. Minus will become plus C intersection with A intersection B, probability of A intersection B intersection C. So as you see here, whenever I'm increasing, like two elements were there, I was having three combination. When I'm having three elements, then this union law is producing 7 elements. So this is nothing but if I'm having n elements here, 2 to the power n minus 1. This is having all combination except the combination which is null event, right? So because of that, the number of combinations which I need to use for calculation becomes very, very high. And because of reason for that, this becomes very difficult to calculate. If there are 5 events, then 2 to the power 5 minus 1. If let's say there are 10 events, then 10 events, if I have to make union, more than 1,000 calculations I have to make. Okay. So which will be cumbersome, which will be difficult. So many times we can use the inverse law here. That is we can use the De Morgan's theorem. So what does De Morgan's theorem says? De Morgan theorem says that probability of A union B, if I take the complement, right? So complement of this, yes, please.
AB bar equal to A bar plus B bar, sir.
Yes. So intersection with. So AB bar is A bar plus B bar, or we can say union is replaced by intersection and individual units are. Similarly, probability of A intersection B whole bar, if I take, and this will be equal to individual bar union with probability of B bar. I'm having difficulty with union, right? So I want to know probability of A union B union C bar. I wanted to know probability of A union B union C. So what I will do, I know that in complement of this will be having probability 1 minus of complement. So I'll take the complement. Now this complement I will open. So this will become probability of A bar intersection probability intersection B bar intersection C bar. And I know that intersection probabilities follows the multiplying law. So I can use it probability of A bar, probability of B bar, and probability of C bar. If you see here, if I'm going to calculate this or this, which one is easier to calculate?
Second one.
Second one, right? Because here I have to do very less calculations, right? Only 3 multiplications. One time I
Excuse me, sir,
subtract.
not audible.
Is it not audible for everyone or?
Sir, you are audible.
Okay.
Audible, sir.
Audible now? Or there is some problem, then should I check my settings or is it fine?
It's fine, sir. You are clearly audible.
Now you are muted, sir.
Sir,
You
now
are
you have
muted, sir.
muted yourself.
Fine. So
Okay, now,
here
sir.
what happens? Am I audible now?
Yes, sir.
So let's say I'm having n elements, right, in parallel or n elements. Is it audio problem resolved, everyone?
Yes, sir. Yes.
Okay. So let's say I want to calculate union probability for n number of elements, right? So what I will do, I'll calculate it 1 minus probability of complement of these events, right? Or this I can calculate as 1 minus multiplication I equal to 1 to n probability of AI bar, right? So which I can calculate as probability of I equal to 1 to n probability of A 1 minus probability of A I, right? So what happens? What is probability of 1 minus AI? What is probability of AI bar? This is nothing but unreliability. So if I want to calculate unreliability, I'll convert that into, if I want to calculate reliability, I'll change it to unreliability, then multiply, then subtract from 1 to get the system reliability. Now this concept is union law is used in the parallel system. Parallel system means the systems which are redundant. That means if I'm having a system where there are two units which are working in parallel, and one of the unit, if they fail, then the system will not fail. Second unit will take over the functions and the second unit will continue to work. Both the units are working. So this is like generally like if we have two, generally let's say we have one antenna, right? From antenna we can have two different cards, two different receivers, R1 or R2. Both are giving the response. So if this receiver fails, then receiver 2 will continue to work. If receiver 2 receiver 2 fails, then receiver 1 will, or if both are working, then also it will continue to work. So how many combinations are there? R1 working, R2 failed. R1 not working, R2 working, and R1, R2. In all the cases, what will happen? The system will work. And what is the case in which system will not work? That is R1 is not working, and R2 is not working, right? Which is this, that for the two systems, I'll take the failure probabilities, I'll multiply them and subtract from 1, I will get the probability that system is working. That will be reliability. If I sum up these probabilities, and if I take 1 minus this, both are going to be equal, because total probability of R1 working, R2 working, R1 not working, R2 working, R1 working, R2 not working, R1 not working, R2 not working, the total sum probability is equal to 1. So rather than calculating 3 combination, because this will require me to calculate 3 combination, rather than calculating 3, sorry, not these 3, these 3, right? I will calculate only 1 and subtract from 1, and that will give me the required probabilities. So this makes this union law simpler to solve if you are able to convert into this formula. Is this understood, everyone?
Yes, sir.
So for parallel
Yes, sir.
system, we can use this, right? Fine. This conditional probability we discussed earlier, but again, I'll try to tell you in a more simpler way what is meant by conditional probability and why is it important? How is it different than the intersection? So there are two probabilities, A intersection B and A given B. Two events are there, intersection event and conditional event. Can you tell me that what is the basic difference between the two? In both cases, both events are supposed to occur, right? But what is the difference in intersection and conditional? Anyone?
Sir, in condition, we know that one event has occurred.
Yes. So how does it change the scenario? In intersection
Sample space will
also,
decrease.
both events have occurred, right? In both, see, whenever I'm calculating probability of A intersection B, that means probability that event A has occurred and event B has occurred. And when I say probability of A given B, that means probability of event that event A is occurring given that B has occurred.
So in case of P A given B, so it is in the time that it is different. It is happening one after the other.
Not necessarily. Not necessarily.
Sir, I think
Both are happening
we are
together, or we can say
we-
both are happening the determined period. Yes. Yes, please.
uh, we are finding the probability based on the other condition event, sir.
Yes, true. That is where the change is. So can you elaborate a little bit more? So
Sir, we are going to find the probability of an event based on the condition of the another event, sir.
true, right, fine. So what is the difference here? Let me explain this in my way. I want to calculate probability of A given B, right? So whenever I say given B, what does it mean? That means B has occurred, or as you told that B is occurred already. It may not be in time sense. It is actually the in the condition sense. That means event B is true. That means if I say event B is true, what does it mean? That my sample space which was there, where all possibilities are there, so many possibilities are there. Now my possibilities are limited only to B. I can talk only about those conditions where B is true. The sample or the outcomes which were belonging to sample space are no longer valid. Only those outcomes are valid where B is present or B is true. So all possible outcomes where events or the sample point of B is coming, then only I can analyze that what is the possibility of A. So what does it mean? B has occurred. That means now B has become sample space. So my sample space probability which was there, whatever was my probability, now I have to divide by probability of B, because probability of B has become 1. Earlier probability of sample space was 1, but by putting that B is true, my probability of B has become 1. So whatever is the probability there, whatever probability I want to calculate, in that always I have to divide by the probability of B, so that the probability becomes, the reference becomes only the B space. Is it understood?
Yes, sir.
Right. Now in the B, what is the chance A can occur? That is only this, the A intersection B. So A intersection B is the area, or is the probability in which A can occur, right? Because now this cannot occur. Outside this area, this event does not exist. This no longer exists, right? So here we take probability of A intersection B, and when we divide by B, probability of B, it will give you the A given B. Similarly, if I calculate B given A, then I will say that A has occurred. So my sample space will change to A only. And out of the A, when B is occurring, that is A intersection B, right? So condition probabilities, when we are calculating, what happens, our sample space is shrinking to that event. And since we're shrinking to that event, our probability space is also shrinking. So we have to reduce the probability space to that event. And we get the same probabilities, but so the difference is in A intersection B, both events are occurring, but our reference point is out of the events from the sample space. That out of all possibilities in sample space, what are the events in which A and B are occurring? But that is our intersection. When we say condition, that means one event has already is present. So our sample space, that means we are only concerned about the event A and B occurring together when B is already there. B is already in where B has to be there, right? So the sample space is now shrink to B only or A only, right? I hope this is clear.
Clear, sir.
Right? So the difference is only in terms in the reference point, that where we are taking the reference. In both the cases, the events are same under consideration. Okay. Let's take one example. The probability of a regularly scheduled flight departs on time is probability that it will depart on time is 0.83, right? And probability that it will arrive on time is probability of A is 0.82. So now when I'm saying probability of right time departure, means out of all flights which are departing from a airport, what is 83% of them depart on time, right? Similarly, when I say probability of arrival on time is out of all flights arriving on the terminal, how but 82% probability is there that they will arrive on time. So 18% will be on not on time arriving, and 17% will be there, which is not arriving, which is not departing on time. And the probability of D given A, D and A, right? D intersection A is 7.8. That means, what does it mean? The probability of flights which have departed on time has also arrived on time. That is 0.78. That means out of all flights which have been departed from a station, and those flights which are departing on time will arrive on time also, that probability is 0.78. But the reference point is out of all flights, right? Now we are interested to know what is the probability that a plane A arrives on time given that it departed on time. So we want that probability of arrival on time given that departed on time. That means now we are considering only those flights which have departed on time. Out of those, what is the probability that they have arrived on time, right? So out of the all flights, how many departed on time? 0.83, right? And out of 0.83, how many are arrived on time? That is 0.78. Okay. Similarly, probability of D given A, probability that departed on time given that it has arrived on time. So if you see that any flight is arriving on time, what is the probability it was departed on time also? That is again 0. Probability that D given A, that is 0.78, but out of the flights which have been arrived on time, that is 0.82. Right? So we can calculate these probabilities, conditional probabilities, which will help us to understand in a lot of data analysis whenever we are doing this root cause analysis, etc. It is very essential that we understand how these conditional probabilities work, because when we say cause is making some effect, then there is some sort of dependency. That means this is leading to this. That means there is some sort of dependency, and if that dependency is there, then we should be able to see in terms of probabilities also. Any queries about it? De Morgan we have already discussed, right? How to use this. So here, like, we can use this example that we have 4 systems, and this will work if component A and B work and either of component C and D work. That means A has to work, B has to work, and either of the C and D, either of the C or D. So what does it mean? A is in series, B is in series, and C or D are in parallel with each other, but they are in series with A and B. Okay. Find the probability that the system works. So I can get this probability. Probability that A is working is 0.9, B is working is 0.9, C is working is 0.8, D is working is 0.8. So how can I calculate? This will be 0.9 multiplied by 0.9. Before that, I will solve this. This how can I solve? I can solve 1 minus 0.8, that is 0.2. Multiply by 1 minus 0.8, that is 0.2. So 1 minus 0.04 will give me 0.96. So the probability of this will be 0.96. If I multiply these three, I will get the probability of system, right? 0.9, 0.9 multiplied by this will give me 0.776. Okay. Now my second problem is I want to know what is the probability that component C does not work given that entire system works. I want to know probability that C is not working given that system is working. Okay. So what does it mean? I want to know that system configuration in which C is not working, but system is working. Okay. So when C doesn't work, what is the probability that system will work? System will work only when A works, B works, D works, but C doesn't work. Okay. Or I can say this is probability of C intersection with system. Okay. System probability. What is system probability? System probability is A intersection B intersection C union D. Right? If I intersect this with C bar, what will happen? This will not impact A. A intersection B will remain same. this inside it will become C intersection with C bar union of D intersection with C bar. C bar intersection with C bar will be how much? Will be null or 0. So what is remaining is A intersection B intersection C bar and D, right?
D.
C bar intersection D. So this I can calculate probability of A intersection B intersection D intersection C bar, right? So 0.9, 0.9, 0.8, 0.2, and probability of system success we already know, we have already calculated. So this gives me the probability that system is working, but component, given that system is working, what is the probability that C will be found in failed state? Yeah. Is it understood? So these kind of things again,
Yes,
whenever we go, yes, please.
Sir, maximum probability in the parallel system, sir, it is nearly 1, sir.
Means I could not get.
So with
Parallel
some
system.
faults also.
Yes, yes.
Yes,
Maximum
sir.
probability in parallel system will be 1 only, right?
Yeah, yes, sir.
In any case, not only parallel, series, whatever system you take, if the probability is not somewhere between 0 to 1, that means you have made certain mistake. Either you have forgotten to reduce this or you have miscalculated.
Yeah. Okay.
It will never exceed 1, right? If it is exceeding 1, that means we have missed this idempotence law somewhere, right? Or the union law somewhere. Is it okay?
Yes, sir.
This is the last slide, then we'll take a break. We have total probability theorem. Total probability theorem says that if let us say I want to know the probability of A, but I know the probability of A when it is occurring with certain, let's say I want to know that what is the A is, let us say taking an umbrella, right? Okay, and E is, let us say there is a rain. Okay, so there's two possibilities that either there is a rain or there is no rain. So whole sample space I have divided in two parts, right? Event that there is a rain, event that there is no rain, right? Now I want to know what is the probability that there is a that someone is carrying the umbrella. So I know that in what cases rain is there and person is carrying the umbrella. Rain is there, person is carrying umbrella. How many cases are there? And how many cases are there? There is no rain, but still person is carrying the umbrella. Okay. So what is the probability of umbrella carrying? Probability of umbrella carrying is probability of this plus probability of this. Probability of umbrella when there is a rain. Sorry, E plus probability of umbrella when there is no rain. And this will give me the probability of A. So probability of any event A, I can get it by probability of that event occurring multiply by probability of event occurring with one part, probability occurring with another part. Here we should know that probability of E plus probability of E bar should be equal to 1. These should be mutually exclusive event. And if there are multiple divisions here, I can take multiple divisions also, but all the events should be mutually exclusive and summation of all the events should be equal to 1. Right? So here E and E bar are the complement event. So their summation, they are mutually exclusive and summation of probability is 1. If there is rain, and there is no rain, both are mutually exclusive. So I can get this probability by, or this E given E intersection A, I can also calculate as E. Probability of this I can calculate. If there is dependent event, I can use it like probability of E, A given E, right? Because as we know here that taking an umbrella can be influenced by the rain, whether there is a rain or not. So A is dependent on E. Since A is dependent on E, this intersection probability I can also calculate by using this formula. That probability of E that there is a rain multiplied with probability of carrying the umbrella given there is a rain, plus probability that there is no rain multiplied with probability that there is umbrella carrying umbrella when there is no rain, right? And this will give me the total probability of carrying the umbrella out of all possibilities. Here the example is taken with two events. This may be multiple events also. Okay. This law is very useful whenever we are doing analysis, because this helps us to understand many scenarios and combine them together to get the individual probabilities. Okay. So many times when we are having multiple cases, multiple machines, multiple equipments which are working, right? Then how do we combine their two probabilities together to get the overall concerned event probability? We can use this total probability theorem. Any queries, anyone? This is also used in this law, which we say that disjoint theorem. Disjoint or which is used for solving the complex problems wherever where we consider one event in two state working and not working, and corresponding to that we calculate the probabilities and multiply to get the system reliability. We are not going to that because that may not be much useful here. Similarly, if we have multiple events like here 5 events are there or k number of divisions are there, then for each one I can take combined intersection probability and sum, we will get the event of A, or I can take the conditional probabilities, probability of B plus multiply probability of A given Bi. If I sum it up, I will get the probability of A. Let's take one example that we have a plant, manufacturing plant, where 3 machines are there, right? B1, B2, B3. Okay. And B1 is producing 30% of the lot. B3 is 2 is producing 45% of the lot. So out of whole production, contribution of B1 is 30%, contribution of B2 is 45%, and contribution of B3 is 25%. And we know that B1, B2 performance is not same. B1 is producing 2% effective, B2 is producing 3% effective, and B3 is producing 2% effective. Yeah. Now we want to know what is the, if let us say out of production, I will pick up one sample. I want to know what is the probability that product is defective. That means out of produced, not what is the probability of defective. I want to know probability of defective. So I can use, I know probability of defective when this is coming from B1 is 0.202, right? Probability of defective when this is coming from machine 2 is 0.03. Probability of defective when it is coming from machine 3 is 0.02. And what is the probability of machine, probability that item will be coming from machine 1? That will be 0.330%. Probability that it will be coming from 2 will be 0.45%, 0.45, and probability that it will be coming from machine 3, that will be 0.25. So now I can use this data to calculate the probability of A or defective. Probability of defective will be equal to probability of B1 multiplied with probability of defective given B1, right? Plus probability of B2 multiplied with probability of defective given B2 plus probability of B3 multiplied with probability of defective given B3. Right? So this will be nothing but 0.02 multiplied 0.3 plus 0.03 multiplied 0.45 plus 0.02 multiplied with 0.25. Right? So same thing can be calculated here. Right? Same thing. And this gives me the probability of, so how much is the defective? Around 2.45% is the defective production, right? There is a Bayes rule. Why we use Bayes rule? Because this is actually Bayes is giving a completely different perspective. Bayes, generally what happens, we try to find out there is generally cause and there is the effect, right? So generally we want to know that effect is dependent on cause. So I'm interested to know the probability of effect. If I know the probability of causes, I will know the probability of effects, right? So this is generally the independent variable. Causes are independent reason and effect is the dependent reason, right? But, and in general, in classical approach, we want to calculate the probability of effect from the probability of cause to effect. But in Bayes theorem, this is reversed. In Bayes theorem, we use the same relation. We know the relation, what is the dependency of effect on the cause. So we are exploiting this relationship to get the probability of cause if I know the probability of effect in terms of probability of effect. So let's say how it is done. That we want to know the probability of independent variable, right? The cause event. And based on what we observed as the outcome. And that is what we are doing in root cause analysis. That is what we mostly want to know, that what can be the responsible reason for a certain kind of event. So we can use this. How do we use this? We want to know that probability of PR given. That means given that I'm observing, like in reference to earlier one, B1, B2, B3, what is the probability that product is coming from machine 2? Let's say R is 2. Given that you have observed a failure, you picked up a product from the population and you found that it is defective, right? You want to know what is the probability that it came from machine number 2, machine number R, right? So we can calculate the same. We know that probability of BR given A is probability BR intersection A divided by PRA, and probability of A, we already know the formula, that is total probability theorem, probability of BI intersection A, summation from I equal to 1 to A, K. Or I can also use this as probability of BI multiplied by probability of A given BI. Same formula which we have discussed in previous slide. Okay. So this probability, I can use this formula to get it, right? Or I can, same formula, if I want to convert this into conditional probability, I can also convert this into the conditional probabilities. So either I can use this formula or I can use, either I can use this formula or I can use this formula or any formula to get the probability that it is coming from a certain machine. So for an example, if we take the previous example, I want to know what is the probability that if I'm finding a defect from the population, that it will be coming from machine B3. Same thing can be done. That say if you have the multiple suppliers, you can, what is the probability that you are getting a product from a certain supplier if you want to get it. So probability that B3 given A is B3 multiplied A given B3 divided by summation of this. So we have already calculated this. If you see that this PA we have already calculated 0.045, 0.0245, and how much is the probability of B3 intersection A? That means probability of B3 multiplied by probability of A given B3. That is 0.005. Okay, 0.005 divided by this, if I take, the value will come out to be 10 divided by 49, or you can calculate accordingly, right? That means out of the 49 product, 49 defective product, 10 product belongs to B3, right? So here we are using the Bayes rule. We are calculating reverse. We are trying to find out the cause probability depending on the what we have observed. And many times this can be used for root cause analysis or various assessments which we can make based on this concept. Fine, we'll stop it here. We'll take a break and then come back again, right? If you have query about this, please ask. Okay, so we have seen like by discussing this, we have also understood that's how to get series system probability, how to get parallel system probability, how to get the combination of series and parallel system probability also, right? Given that if we have the element probability, we have also seen that how can we get the probability when multiple scenarios are there, how can we combine them together to get the overall probability of a particular event by using the total probability law. Yeah.
Please switch on your cameras.
Yes. Vijay, you are saying something?
Yes, sir. Actually, I'm saying
Sir,
yes.
sir, maybe law से PPT slide sir.
Yeah, I've just stopped that. I've moved to another window, right?
Okay.
So we'll take a break. I think it is already 8:22. So let's take a break for 10-15 minutes. I'm not able to speak continuously lot, right? So still not more than 1 hour, but still I'm continuing lot. Fine.
Yeah,
So we'll take a break.
Actually, right. Fine.
If you have any query you want to ask, you can still ask.
So during the break, one can post in the chat box.
Yes.
Just after the chat box, we will take the queries.
Whatever may not be related exactly to this, right? If you have somewhere far-fetched also, you just put it. We can discuss. Yeah. Related with relativity calculation, whatever. Okay. Fine. So we'll take a break. Then we will start discussing a little bit about the distributions, right? How what are they, and how they are used.
So it's 8:35 or 8:40?
10 minutes is enough, right?
10 minutes. Okay. 8:35. We will start at 8:35.
Let's meet at 8:35. Fine.
Yeah.
Thank you.
Okay. Thank you.